let's go on my last slide. Well, I just need to solve the issue of heteroscedasticity. Well, under Gauss-Markov assumption, plus an assumption on the error term, just normal distribution of our error term, it turns out that OLS estimators are the best one, are the blue one, so are the best linear unbiased estimators. Well, under Gauss-Markov assumption, there is a nice word, because we assume that the error term is almost scedastic. Sorry. However, when we state this kind of stuff, I'm telling you that the variance of the error term does not depend on the regressor. However, I cannot state this kind of stuff here, so I cannot use the OLS, because since I could use OLS, but my OLS at the end of the day is going to be something different from the Gauss-Markov OLS, because I cannot state the homoscedasticity. So, assuming independence in the sample, and we had a sample of independent observation, because at the beginning we selected Freddie Mac provided us a sample of 22 million of fixed rate mortgages. However, we just randomly picked 50,000 loans. So the random sampling at the end of the day has to ensure, and this is our expectation, the random picking is going to ensure us that our observations are going to be independent. I'm not gonna go deeper in the maximum likelihood estimation, because honestly our machines nowadays can do this in just a few seconds. But I wanna tell you something more. Well, when we get the estimate for the coefficient by using the maximum likelihood estimation, actually we tend to maximize this function. So the maximum likelihood estimation is gonna give me the betas that are able to maximize the probability of observing a sample that I have already observed. So I'm implicitly telling you that this function can be always maximized, but it's not like that always. Indeed, it turns out that under Weierstrass theorem, a function can be maximized if this function is well defined in a specific domain. Well, it turns out that my log likelihood function here, this one, where pi is just the link function, the value that the link function gives me given x times beta. This function is well defined because my maximum likelihood estimation function is gonna give me always an outcome that is a probability, so that is strictly between 0 and 1. Since this function is well defined, and since this function satisfies the Weierstrass theorem, I can state that this function can be always maximized. And if this function can be always maximized, this function will be always able to give me an estimation given the maximum likelihood estimation. Now, we want to go deeper in the practical application. So Basilio is going to explain you the data set, and after that I'm going to explain you why and how we act in order to get a model biased data.
So before starting to talk about the data set, remember that our U is the probability of default of the client. So we want to through our model to predict this probability of default. So if the client will default at the end of the day or not. So the goal, as I said, is developing a scorecard using data derived from the Freddie Mac single family loan level dataset. The full version of this data contains approximately 22.19 million fixed rate mortgages originated between January 1, 1991 and June 30, 2015. However, we decided to take a sample of 50,000 loans from a particular origination cohort, so in 2007. So we are 2007. Using data that was riddled with error could give us a seriously detrimental impact on our analysis. So we decide to remove some observation from our dataset that appeared to have been coded incorrectly, or they missed for some important values in the observations. So in order to understand what will come in the next slides, I would like to do a brief introduction. So let's imagine the professor comes to us asking for a loan of $1,000. So we are at time t, and professor comes to us. At time t, we have the origination data. So we have, what is the origination data? It is the set of all the information that professor gives us when he asks for the loan. how does it work in reality? In reality, we are considering just two times, a range of time between t and t minus k. So we, throughout the observation we have to decide if we give money to the professor or not. We try to match the information the professor gave us with the information, similar information of an historical borrower, in order to predict a model which goes from time t to time t plus k, which is able to tell us if the professor will default or not. In our construction of the model, it works in a different way, because we don't consider the range of time between t and t minus k, but we just consider this range of time. So we have to construct a model, but why we can do it? Because we have not the information at the end. But in reality we have, because we have the other set of data, so the performance data, that at time t plus k tell us if the professor has defaulted, if the professor has not defaulted, but tell us also the behavior of the professor during the time, so also the frequency of payments of the professor. So, as I say, we have two sets of data. The origination data for summarizing everything. The origination data tell us, okay, the information are good, you should give money to the professor, because the information, it could be a good client. After that, we construct a model which predicts the probability of the default of the professor during this time, and that